So good morning everybody. So today we will be solving this complex RC circuit. So it's an RC circuit, but it's a complex one. Why it's a complex? Because this is not similar to a simple RC series circuit. If I close the switch here, I have an EMF and I have 3 resistors, and these 3 resistors are not connected in series, are not connected in parallel, so I cannot simplify it to a simple circuit. The simple circuit, I remind you, that's something like this. That's an EMF, that's C, that's R. I cannot simplify it to this. So this is not equivalent to that. So what I can do in this situation, if I close the switch, what I will do, I will charge a capacitor. And we know that the charge of this capacitor, if I call it Q, the charge of this capacitor, it will increase in this fashion, exponential fashion, until reaching Q infinity. The difference in potential across the capacitor, call it delta VC, it increases in the same fashion, and this is, we call it delta V infinity. Why it's not the EMF? Well, because that's not a simple circuit. Last one, we know that the current flowing in the capacitor here, it starts from a certain value and it decreases exponentially until reaching 0 at infinity. So that's the current, and this I call it I node. Why it's not epsilon over R again? Because this is not a simple circuit. And also, we don't know what is the time constant, tau. What is tau? Is it R times C? No. So what we can do? Well, we can do a lot of things. We know that when the time equal to 0, the charge is 0 and the difference in potential is 0. So what we can gain from that? Let's see. When the time is 0, so here I close the switch. When the time is 0, the charge is 0 and the difference in potential is 0. The charge is 0 and the difference in potential is 0. So if I draw this capacitor here, and I am saying that this difference in potential here is 0, what it means? It means that these 2 points, they are at the same electrical potential. So we have the first point here, the second point here, and these 2 points, they are at the same potential. What it means? It's like there is a wire between them. It's as if there is a wire between them. So I can draw the same equivalent circuit at t equals 0. So instead of having a capacitor, I draw a wire. R here, and the EMF here. What we don't know actually, if I come back to the next slide, at t equals 0, I know the voltage, I know the charge, I don't know the current. So let's calculate this. All right, so what is this current? That's the current flowing here. So that's the current flowing here. Can I calculate the current flowing here? Well, that's from circuit. That's easy. What is the current? Well, I need to simplify the circuit more. I need to take the equivalent resistor here because these 2 resistors are in parallel. What is the equivalent? R over 2. I can calculate the total current in the battery. That's E over the equivalent resistor here. The 2 resistors are in series. So R plus R over 2, E over 3R. That's the current in the battery. That's the current here. All right, so I know the current, what I can calculate. I I can calculate the potential here. So that's simple circuit problem. That's the resistance R over 2 times I. What is R over 2 times I? If you do that, you get E over 3. Now, here we are done. So we know this voltage. Where is this voltage? Is here. And I want the current circulating through capacitor. That's the same current circulating through a resistor. Is the voltage E over 3 over R. So that's E over 3R. All right. So we calculated the current, the initial current in the capacitor. So if I come back here, what is this initial current? E over 3R. Now let's move to the next interesting point. The next interesting point is when t equal, so that's t equals 0. The next interesting point is when t equal infinity. We know, what we know at t equal infinity, we know that the current is 0. But we don't know the charge, we don't know the potential across the capacitor. So let's move here. So at t equal infinity, the current in the resistor is 0, this current. I have a capacitor, and we are saying that the current is 0. When the current is 0 through in the wire, what it means? That's a broken wire. That's a broken wire. So I can again here draw my circuit. Okay? That's E, R, R, and here another resistor, and here I have a broken wire. Good. So I can draw even more simple circuit like this. That's the simple circuit. Okay. So what we are looking for, we are looking for what we can calculate here in the circuit. We can calculate difference in potential. Delta V, that I call it infinity. We are saying that the current here is 0. If the current here is 0, what is difference in potential through this resistor? Is 0. So what is difference in potential through the capacitor? That's exactly difference in potential through this resistor. So this is V infinity. This is delta V infinity. Okay? All right. And I know how to calculate this. All what I need to know to calculate the current in the battery. So the current in the battery, what is it? E over the equivalent resistor to R. So what is delta V infinity? It follows easy. That's the resistance times the current. So it's what? E over 2. Half of the EMF in this situation. What is the charge in capacitor? Well, that's capacitance times the difference in potential across the capacitor. So this is C E over 2. Wow. So let's come back to the first slide. What we know that this equal to E over 2 and this equal to C E over 2. We are almost done. We found a lot of things, isn't it? So just by equivalent circuits, by treating just the 2 point, the 2 characteristic point, t equal infinity and t equal 0, we deduce the initial current in a capacitor and the final voltage and the final charge. Well, so we deduce almost the shape. What is remaining is the time constant, and here there is a trick, there is a mathematical trick. Okay, so what we can do with time constant? What is the expression of the charge? How does charge vary? We know this. It varies the same as an RC circuit. Always during charging of any capacitor, we have this. The charge equals charge infinity 1 minus exponential minus t over tau. That's the charge in capacitor. But it's the current in the capacitor. The current in capacitor, dq over dt. Did you try to derive this in lecture? So you should. To derive this, you get q infinity over tau. The minus with the minus will cancel out. Exponential minus t over tau. But how we write this in class, in lecture? I naught, the initial current, exponential minus t over tau. So from this, what you can deduce? That I naught is equal q infinity over tau, which means the time constant is the infinite charge over I naught. As simple as that. So let's come back now. The charge, so tau is equal to the charge infinity over current I naught. If you do that, CE over 2 divided by E over 3R, you will get 3/2 RC. So we know all the characteristic of this capacitor during the charging process. Alright, so here I summarized all what we found for this circuit during the charging process. So can we write the equation of charge? Of course, Qt equal Q infinity 1 minus exponential minus t over tau, and the current I naught exponential minus t over tau. And you have everything here. All what you do is just to replace. So for example, if I see the charge is equal to the infinite charge, CE over 2, 1 minus exponential minus t over tau. So the inverse of tau, you get 2 over 3 RC. That's how the charge of this capacitor vary with time during the charging process. So thank you for watching. See you in my next